Hi students, in this video we shall learn about the Sn1 mechanism, that is substitution nucleophilic unimolecular. It is called as Sn1 mechanism because it follows the first order kinetics. That is rate of reaction depends upon the concentration of only one reactant. So it is called as unimolecular because it follows the first order kinetics, that is the rate of reaction here depends upon only the concentration of only one reactant. Now this Sn1 reaction are generally carried out in polar protic solvents. Sn1 reactions are generally carried out in polar protic solvents. Examples are like water, alcohol, etc. Then what are polar protic solvents? Polar protic solvent means they contain at least one hydrogen atom connected directly to the electronegative atom. Now here polar protic solvents means, I will just write the definition here. Polar protic solvents, it contains at least one hydrogen atom connected directly to an electronegative atom. That means H is connected to electronegativity atom, that is hydrogen or nitrogen, etc. Did you get my point here? That polar protic solvents are, it contains at least one hydrogen atom connected directly to an electronegative atom. Here hydrogen is connected to electronegative atom, that is oxygen. Here hydrogen is connected to electronegative atom, that is nitrogen. Likewise Sn1 reactions are carried out in polar protic solvents. So here water is an polar protic, alcohol is a polar protic solvent. These reactions are carried out in polar protic solvents. Now we shall consider the example of the reaction between tertiary butyl bromide and hydroxide ion in the Sn1 mechanism. Here the reaction between tertiary butyl bromide and hydroxide ion. Now we can see the reaction here. I have already said to you the reaction between tertiary butyl bromide and the hydroxide ion. Tertiary butyl bromide, it is tertiary butyl bromide and hydroxide ion. Now I have already said in the nucleophilic reactions the nucleophile will go and attack the carbon. Now the product will be formed as OH plus Br minus. This is the reaction of Sn1. See, it is a, I'll just name it 2-bromo 2-methyl propane. Now we have got here 2-methyl propane 2-ol. Now see here, it is a tertiary butyl bromide. Tertiary butyl bromide. It gave tertiary butyl alcohol. The reaction between tertiary butyl bromide and hydroxide ion will yield tertiary butyl alcohol. This is the reaction of Sn1 and it follows first order kinetics. See, this is the reaction. Now we shall see the mechanism. Here the mechanism is 2-step. In the Sn2 it is only 1 step. Here it is 2 steps. This Sn1 mechanism occurs in 2 steps. First step, step 1. Here the polarized CBr bond undergoes slow cleavage to produce a carbocation and a bromide ion. Here first tertiary butyl bromide undergoes slow cleavage. So Br forms a leaving group. Halogen forms a leaving group. Here Br is a leaving group. Now it forms a slow cleavage to form a carbocation. See, here is a carbon. This carbon, and here it is CH3, CH3, CH3 plus Br minus. This carbon gets a positive charge, that is, it is a carbocation. It is electron deficient. It bears a positive charge. These are electron deficient, having only 6 electrons. 1, 2, 3, 4, 5, 6. The carbon is having tetravalency. It should have 8 electrons. That is 4 bonds, 8 electrons. 1, 2, 3, 4, 5, 6. Here only 6 electrons. That's why it is a carbocation. Carbon bearing positive charge. These are electron deficient. I will just write it here. Carbocation means bears a positive charge and electron deficient. Here Br is a leaving group. Now we shall see step 2. Here what happens in the step 2? Carbocation is formed, is then attacked by nucleophile in step 2. Here see, I have already showed you that there is a formation of a carbocation in the first step. CH3, here is a carbon atom, CH3, CH3. Attack of nucleophile, that is hydroxide ion, will result. This is step 2. CH3 thrice COH. It completes the second step and it also completes the substitution reaction. In the second step, the carbocation is formed. No, it is attacked by the nucleophile in the step 2. Now in step 1 and step 2, step 1 is the slowest and it is also reversible step. Step 1, it is step 1, no? Step 1, it is slowest and it is reversible. Step 1 is the slowest and reversible. Now the next point is the carbon Br bond breaking for which the energy is obtained through solvation of halide ion with the proton of protic solvent. The carbon Br bond breaking for which the energy is obtained through solvation of allyl ion with the proton of protic solvent. I have already said that Sn1 reactions are generally carried out in the polar protic solvents. The Cbr bond breaking energy is obtained from the solvation of halide ions with the proton of protic solvents such as water, alcohol, etc. The energy is obtained for breaking from the polar protic solvents. Here the next step and the next point. In every reaction, the rate of reaction depends upon the slowest step. In the Sn1 mechanism, the slowest step is step 1, that is CH3 tries Cbr. It is reversible also and formation of a carbocation. Here the rate of reaction depends upon only the concentration of alkyl halides, this one, and not on the hydroxide ion. So because it depends only on the slowest step, the slowest step is this one. So it depends only on the concentration of alkyl halides or not on the hydroxide ion. This is the next point. The order of reactivity is like this. The tertiary halides are more reactive than the secondary halides. The secondary halides are more reactive than primary halides. Then comes the CH3X. Here, the greater the stability of the carbocation, greater will be its ease of formation from alkyl halides and faster will be the reaction. Greater the stability of carbocations, that means tertiary halides carbocations are very stable. That is because tertiary carbocations are more stable because presence of more CH3 groups distributes its positive charge. It distributes its positive charge with these 3 CH3 groups. So it is very stable. And the next point is tertiary alkyl halides undergo Sn1 reaction very fast because of stability of tertiary carbocation. I have already said the stability of carbocation. Tertiary carbocations are more stable due to the presence of these CH3 groups to distribute its positive charge. So tertiary halides are more stable here than the secondary halides. Then comes the primary halides. It is the order. Due to the presence of carbocation, allylic and benzylic halides also show high reactivity towards the Sn1 reaction. Allylic, benzylic halides show high reactivity towards Sn1 mechanism. Do you know what is allylic halide? I will just write it here. CH2 double bond CH, CH2X. Here you can observe that carbon is bonded to a carbon, that is doubly bonded to the other carbon. Here is a carbon which is bonded to the carbon, singly bonded to the carbon, and this carbon is doubly bonded to the other carbon. Such a carbons, for the first carbon it is attached, halogen is attached. So such type of halides are called as allylic halides, that is carbon is bonded to carbon, that is in turn doubly bonded to the other carbon. Here is a halogen, it is allylic halide. Here the carbocation formed in the allylic halide by the removal of halogen. I will just show you CH2 double bond CH, CH2X. If the halogen is removed, it will become CH2 double bond CH, CH2 plus. These are stabilized by the resonance. I will show the resonance of this CH2 double bond CH, CH2, and this bond is shifted to here. This is the resonance symbol, and CH2, here it becomes a single bond because the bond is shifted towards this side. CH2, this bond is shifted towards this side, and here you can observe the carbocation. In the first, here is the carbocation, in the second, here is the carbocation. It is stabilized by the resonance. And in the benzylic, it is a carbocation. This bond is shifted towards here first, and after the shifting of the bond, this bond comes here. See, I have shown you here. This bond comes here, it becomes CH2, and other bonds remains in the same position like this. And in the second, this bond is shifted towards here. Here the positive charge is obtained, and the next, this bond is shifted towards this side, and this bond is written as it is. Here we get a positive charge, that means electron deficient, CH2. And after this bond is now shifted towards this side, and we will get a positive charge here. These are stabilized by the resonance. It is a benzylic halide. The order of reactivity of the halides follows the same order in both Sn1 and Sn2. That is, the first is Ri, the second is Rbr, and the third is Rcl, and the fourth is Rf. Here the Iodine is less electronegative than the fluorine. That is, what is electronegativity? It is the tendency of atom to attract a shared pair of electron towards itself due to the ion here. Now, for a given alkyl group, the reactivity of alide Rx follows the same order in both mechanisms, that is Sn1 and Sn2. The order of reactivity of halides is same. First is Ri, next is Rbr, next is RCl, next is Rf. This is because of electronegativity. What is electronegativity? It is the tendency of the atom to attract a shared pair of electron towards itself. Here, due to the large size of iodine, it will be released at faster rates in the presence of incoming nucleophile. So it has less electronegativity than the fluorine, bromine. So it has very large size. Due to large size, it will be released at faster rates in the presence of incoming nucleophile. It is all the explanation about Sn1 mechanism. Please subscribe to our channel.